So why did I emphasize in the previous slide? Let's imagine there is some single machine that can immediately calculate the inner product between xi and xj, or the kind of inner product with sigma p covariance matrix. So I can explain this using this slide. Let's imagine a very simple linear regression function in this 2D space. Let's say this is a training data point. So here x is one-dimensional single line, and this is y-axis. And so we want to make a linear regression that can fit everything very well, right? But immediately we can notice that this simple linear function wx cannot fit all the training data point well. Linear regression has usually high bias because of the simple form function. So to deal with such a very complicated training data point compared to this simple linear form, some researchers tried to expand the input space using a feature mapping. So instead of simply use x, we can expand this feature space to like 1x, x squared, x cubed, and so on. Then we have 5 features. So we can define 5 different parameters for each element. And then the linear regression becomes more complicated. We have 5 different elements, so we have 5 different parameters, and this linear regression can be more flexible and can fit this training data point very well. With these 5 expanded features, we can fit all the training data points without any error. So with such feature expansion, even with this simple linear regression technique, we can fit every training data point. Okay, so this is called feature expansion and very useful technique. Do not use the original input x, but use some expanded. So you can transform the input x to other shape. That is absolutely fine. That is very useful technique, and I recommend to consider this kind of technique. But the problem is, it is still unclear how to expand the feature, how to define this kind of another features from the original x. And also, usually when you increase the number of features, the danger of overfitting also increase, right? And it's also very inconvenient. Define expanded feature and compute something and then make a prediction. That also inconvenient. Kernel method and kernel trick is very interesting idea, which define a similarity between input, and so it's kind of inner product between two embeddings, okay, two feature maps, right? So we can denote this extended feature using pi x. Okay, so from original x, we can expand x to more higher dimension, and define k, the kernel function, as an inner product between two expanded feature vector. But when we can directly define this kernel function, indeed we don't need to find this feature map to figure out the inner product between pi xi and pi xj, psi xi and psi xj. Instead, we can just compute this kxi xj using a closed form equation like a RBF kernel function. Okay, RBF kernel function is one of the most famous kernel function in many places, which just simply compute the inner product between two expanded features using this exponential minus xi minus xj normed square over 2 sigma square. So this is an inner product between two expanded features. And graph matrix K is a matrix consists of this kernel function output between all the pair. And in the previous slide, so this part will be replaced by a kernel function like RBF graph matrix. So this part will be replaced by RBF kernel graph matrix, and this part also easily filled with kernel RBF kernel function. And all part can be easily computed from the RBF kernel function. So one nice thing of this kernel trick is, indeed this RBF kernel function utilize infinite dimension feature expansion mapping. And we don't need to know the exact feature mapping function. Kernel mapping can directly tell us very complicated feature expansion and inner product processing by this simple closed form equation. Very convenient, powerful approach. So using this RBF kernel, we can easily define flexible function for any dimension, for any type of input. And it turns out this kernel method shows very nice performance.